Hello there and welcome back to the Science Sleepy Minds. Above you the sky's velvet black but not empty. There's a pull behind your chest, like gravity just remembered it, left the stove on and came rushing back with vengeance around you. Stars smear into streaks of light, time twists like wet fabric, and space itself, whatever that really means, starts to whisper goodbye. You're not floating, you're falling, but not down, inward. Into what? Well, that's the thing. No one knows exactly. You're falling into a singularity. Yeah, you probably won't survive this. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're at it, drop your location and local time in the comments, because I'm guessing where you are, space is still behaving. For now. Dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You don't feel it right away. The laws of physics don't come crashing down in a blaze of sci-fi theatrics. They unravel slowly, elegantly, like a piece of thread tugged from a sweater you didn't realize was made of one continuous strand. You're drifting closer to a place where mass isn't just heavy, it's unreasonably, cosmically inconsiderate. A place where gravity doesn't simply bend space-time, it obliterates its to-do list. At first the pull feels manageable, like sinking into a warm bath, but then you realize this bath is infinite, and the drain isn't at the bottom, it's in the middle of reality itself. A singularity isn't just dense, it's where density goes to scream into the void. 1 point, 0 volume, infinite mass. The math throws up its hands and says, nope, I'm out. The singularity is the end of space-time, not just the end of your story, but the place where stories stop making narrative sense. Historians still argue whether early descriptions of dark stars in the 18th century hinted at what we now call black holes, or if it was just Newtonian bravado mixed with a poetic fear of the unknown. Regardless, the idea's been lurking in physics longer than relativity. Now, you're skimming the edge of this idea and suddenly, direction feels optional. There's no down anymore, just in. Your clock is ticking slower, but from someone else's view, if anyone could survive out there to watch, it would look like you're frozen just above the edge, eternally pausing right before the drop. That's time dilation for you. It's dramatic like that. This moment, right here, is probably the last time you'll be part of what we casually call the universe. You're at the edge of the event horizon, which we'll probably meet soon, but here's the spoiler. Everything that happens next is technically outside the observable universe. Even light can't crawl back out. Not because it's lazy, because gravity here is so greedy, not even photons get a say. Some physicists joke that falling into a singularity is the universe's version of Control plus Alt plus Delete. It's an ungraceful reboot. Others think it's more like tearing the motherboard in half while it's still running. Depends on your level of optimism. Meanwhile, the structure of space-time, the smooth, elegant grid Einstein so lovingly described, is starting to wobble like a bad Wi-Fi signal. Oh, and by the way, there's no turning back. The escape velocity at this point exceeds the speed of light. Unless you've got a warp drive tucked in your sock, this is a one-way ticket to gravitational absurdity. And no, calling your mum won't help. Cell reception ends at the edge of reason. Still, it's not all doom and gloom. In 1965, Roger Penrose mathematically proved that once certain conditions are met, like enough mass in a small enough volume, a singularity must form. That got him a Nobel Prize for discovering something no one can see, reach, or survive. Academia is wild. Back to your fall, things get quiet here. Not because there's no sound, though yes, space is famously not chatty, but because your thoughts are slowing, stretching. Light around you is redshifting, pulling toward the infrared like it's tired of all this visible spectrum nonsense. You're seeing the universe from a vantage point no telescope can ever reach. For a brief moment, you are an observer of the infinite, and it's not exactly inviting. Curiously, some old texts suggest ancient cultures may have sensed the idea of an all-consuming cosmic pit. There's a fringe theory involving Babylonian astronomy and the mouth of the dragon, a mythical region in the sky thought to swallow stars. Historians still debate whether this was metaphoric myth or a poetic attempt to describe something darker. Either way, they weren't wrong. As you fall, you start to feel thinner. Not physically, yet, but conceptually, like your idea of self is becoming less relevant. Here, individuality doesn't survive. Information itself starts to break down. And speaking of breakdowns, this is where general relativity, the king of cosmic rules, starts panicking in the corner. Its equations work beautifully until this point. Then they divide by zero and burst into metaphorical tears. You're no longer a person. You're a collection of probabilities navigating a geometry that doesn't behave. It's not that reality ends here, it's that the rules to describe it stop working. Like trying to explain modern internet culture using only a medieval cookbook. Before the full plunge, here's a fun fact to ponder. The centre of the Milky Way hosts a singularity, Sagittarius. A star, a supermassive black hole, sits 26,000 light-years away, silently shaping the galaxy. It's been eating stars for billions of years, and it might even burp them out as gravitational waves if it feels cheeky. So, as you continue drifting into this impossibility, remember, you're not alone. Singularities aren't rare. They're everywhere, quietly waiting at the centres of galaxies, in collapsed stellar corpses, maybe even lurking in hypothetical microforms. You're just one of the few lucky enough, or unlucky, depending on your current velocity, to experience one up close, and you've only just crossed the threshold. You're not tumbling now, you're gliding almost politely deeper into the gravitational well, as if the singularity has decided to give you a moment of calm before the chaos resumes. But don't let it fool you. Around you, the very structure of reality is groaning, bending and twisting in ways your brain isn't equipped to process. You can almost hear it, a low, slow creak, like the hull of an old wooden ship straining against a rising tide. Only this tide is made of space-time itself, and it's collapsing inward. Einstein once described gravity not as a force, but as a curvature in space-time. Imagine laying a bowling ball on a trampoline. That's the classic analogy a planet or star causes a dip, and smaller objects roll toward it. Neat and intuitive. But here, you've got more than a bowling ball. You've got a runaway elephant made of collapsed mass stomping through the trampoline, punching a hole through the middle and tearing the edges. No elegant curvature, just obliteration. You're approaching a place where the very fabric of reality is being unstitched, that trampoline isn't bouncing back. And here's where it starts to get weird. Normally when space-time bends, say near a star or even a planet, you can still define coordinates. You can map things. X, Y, Z, time. It might get tricky near extreme masses, but the math still plays along. But close to a singularity, the math starts playing Monopoly with Uno rules, and suddenly the coordinates collapse into a singular point. No width, no height, no depth. You're inside a system where location and when are no longer distinct. They become smeared together like wet chalk on a blackboard. Historians still argue whether we should think of a singularity as an actual place, or just a breakdown in our current understanding. Some physicists suspect it's not a spot at all, but rather a flaw in the equations, a red blinking light that says, "Physics error. Please update software." And the thing about errors, they ripple. As you move inward, the metrics that define space, like distance and direction, start to melt. The concept of volume loses meaning. You feel yourself stretching in time, shrinking in space, and being twisted in dimensions you didn't know were there. Imagine trying to measure water with a ruler. That's what it's like, trying to make sense of gravity near a singularity. Except the water is boiling, the ruler is melting, and you're not sure you're still a physical object anymore. Meanwhile, Einstein's field equations, the things that describe gravity's effect on space-time, are shrugging their shoulders. At the singularity, those neat tensors and stress-energy relationships become undefined divide by zero, end of story, or rather, beginning of something else. And yet, even here, you're surrounded by echoes of science's stubborn optimism. In the 1930s, Oppenheimer and Snyder predicted this gravitational collapse using Einstein's equations. They followed the math down into the rabbit hole and realized, hey, stars don't just die. Under enough pressure, they collapse inward forever. No explosion. No phoenix moment. Just an implosion of mass into what they called a frozen star. That was before the term black hole became popular, before we truly understood just how final that collapse could be. Back to you. The light around you has stopped behaving. It's not just bending, it's spiraling, looping in orbits that shouldn't exist. Photons are getting caught in gravitational whirlpools. You're seeing your own back like a space-time selfie gone wrong, and yet, somehow, it's beautiful, like being caught inside a fractal. Patterns within patterns within patterns. Some ancient thinkers believed that geometry held the secrets of the universe. Euclid would have cried if he saw this. And maybe you feel it in your chest now. Not pain, not fear, just a profound sense of disassembly. The way a building feels in the final second before demolition. Not yet rubble, but no longer structure. That's you. You're not falling anymore. You're becoming part of the fall. A ripple. A twitch in space-time's final breath. Curiously, some fringe ideas, mostly from the early 20th century, suggested that black holes might not end in singularities at all. Some thinkers imagined core bounces, where instead of compressing infinitely, the collapsing matter rebounds, kind of like a cosmic trampoline refusing to tear. This idea, known as a bounce cosmology, is still debated. Historians of science argue whether it was driven more by hope than evidence. Still, it's a comforting image, isn't it? That even here, in the belly of gravitational doom, the universe might be plotting a way to bounce back, to start over. Meanwhile, every second for you is a century for someone watching from afar if they could still see you, which again they can't. They'd see you frozen near the edge, stuck in an eternal descent. But you're accelerating, falling through a space that no longer resembles anything from your waking life. Forward, inward, faster. Not toward a centre, but toward the end of context itself. And now something strange is happening to time. It doesn't tick, it flows, but sideways. It stretches, then loops. You try to hold on to a thought, but it folds in half before you finish. Are you thinking in sequence? Or remembering the future? You can't tell. The singularity doesn't care. Out here, Newton would have thrown his apple. Galileo would have stared at the falling mass and whispered, "Nope." Even Einstein, who gave us this weird trip, might have blinked and muttered, "I didn't mean this." And you're still you. Sort of. But your concept of self is being smeared into the structure, or what's left of it. The further you go, the more your atoms cease to matter. Matter itself is losing meaning. Your quarks and leptons are still dancing, but the stage beneath them is unravelling. There's no backstage, no exit, and still, you fall. You're deeper now, past the place where light folds, past the point where time stops cooperating. The blackness around you isn't absence, it's density. Gravity here doesn't just pull, it compels, it instructs. It rewrites the laws you once trusted to keep your feet on the ground. Except there's no ground. Not anymore. Welcome to the inner sanctum of impossibility. And here's the headline. The singularity is not at the event horizon. That was just the velvet rope at the entrance. Now you're on the guest list, right inside the main act. The cosmic trick that defies definition. And the headliner? Gravity. In its most theatrical, mind-bending form. What you're feeling now isn't acceleration. It's disobedience. Gravity is no longer behaving as a force that merely pulls you downward. It's doing a full magic act, compressing your mass, stretching your sense of space, and scoffing at Newtonian logic. Honestly, Newton's apple would have been vaporized into theoretical pulp 5 seconds ago. From where you are, the very idea of mass becomes negotiable. Matter collapses inward with such intensity that the distinctions between thing and place blur. Remember that beach ball you left on Earth? It still obeys classical mechanics. You don't. You've become part of a mathematical abstraction. Let's talk about the black hole's favourite party trick, time dilation. Out there, from a safe cosmic distance, someone watching you would think you've stopped moving entirely. You'd appear frozen just above the event horizon, locked in some eternal approach that never quite happens. That's because, for them, time outside keeps ticking. But for you, in here, time has unravelled like yarn dropped into a singularity-shaped blender. Here's a fun quirk. The closer you get to the singularity, the more pronounced this time distortion becomes. From your perspective, everything else in the universe seems to speed up. Stars are born and die, galaxies rotate, civilizations rise, fall, meme and collapse. Billions of years pass in what feels like a blink. You're watching time collapse from the wrong side of the glass. In 1916, Carl Schwarzschild provided the first exact solution to Einstein's equations of general relativity, while on the front lines of World War I, no less. His solution described a non-rotating, uncharged black hole, now called a Schwarzschild black hole. That solution planted the seed for understanding how time and space become twisted beyond recognition inside such a cosmic monster. But of course, that was a simple case. Add some spin, maybe a little charge, and suddenly the geometry inside gets spicy. You're not just falling, you're spiralling into something that may not even be a single point. Some physicists propose a ring singularity in rotating black holes, a loop, not a dot, which opens up possibilities. Possibilities like wormholes, shortcuts, escape hatches, but we'll save that for later. For now, let's enjoy the show. As gravity compresses you, your atomic structure starts to change, not metaphorically, not poetically, literally. The pressure is so extreme that electrons get shoved into protons, forming neutrons. You are becoming neutron matter A collapsed star's lunch. If this were a neutron star, you'd stop there. But this is worse. Here, not even neutrons get to keep their job. Everything is being crushed beyond the limits of known physics. But you're not alone in this collapse. You're in good company. Crushed stars, rogue planets, fragments of interstellar gas, unlucky photons, all converging toward a point that doesn't even occupy space in the usual sense, a single dot with zero volume and infinite density. At least that's what the math says. That's the trick. The equations allow this infinite density, but they don't explain what it is. It's like asking your calculator to divide 1 by 0 and expecting a paragraph of answers. You'll just get an error message, maybe a sigh. Still, not every physicist is satisfied with error. Some think the singularity isn't real in a physical sense, just a sign that our theories break down at this scale, a placeholder for something more complex we haven't figured out yet. Historians still argue whether singularities are physical realities or just the universe flipping us the theoretical bird. And right about now, you're starting to feel the singularity's most disturbing effect: gravitational lensing from the inside. Light paths curve so drastically here that you begin to see things behind you and in front of you. At the same time, imagine looking forward and seeing the back of your own head. Not because mirrors are involved, but because light itself is doing donuts in space-time. Everything feels slow and fast all at once. You get the sensation of stretching, a vertical tension you can't resist. This is what astrophysicists lovingly call spaghettification. Your feet, or whatever was once your feet, are feeling gravity slightly more intensely than your head. The difference grows as you fall deeper. Soon, atoms aren't being kept together the way they were. Bonds break, nuclei snap. The very forces that glue matter into shape begin to fail, but you wouldn't notice the pain. You wouldn't even call it sensation. You're moving toward an existence that can't be described with biology, or neurology, or even science as we currently practice it. You're being drawn not just into a region of space, but into a place in physics where causality might disintegrate. And yet, in this absurdity, there's a certain peace. Maybe it's the silence, maybe it's the weightlessness, or rather, wakefulness, the feeling of being, held entirely by gravity, no friction, no noise, no resistance. You are one with the pull. If you could radio back just one signal, it might sound like static or maybe a blip, like the kind LIGO detected in 2015 when two black holes merged and sent out a ripple. That wave, travelling across the universe, told us something monumental had happened. Maybe someone will detect your ripple, a whisper from inside the fall, or maybe not. The universe, after all, doesn't guarantee answers, only questions wrapped in increasingly inconvenient gravitational puzzles. There's no warning, no obvious threshold, you just are across it now, the event horizon, though it doesn't feel like anything changed. No alarms, no sci-fi whooshing sounds, just the quiet certainty that there is now no way back. You've stepped off the edge of the map and into the region marked with a polite cosmic, "Here be nope." This is the event horizon, the invisible boundary that surrounds a black hole like the world's most sinister velvet rope. Cross it, and escape becomes impossible, not just for you, but for light itself. Not because the light slows down, it can't, but because the fabric of space-time is curving inward faster than light can travel outward. Imagine trying to swim upstream in a river that's flowing faster than you can possibly swim. Even the best lifeguard in the cosmos isn't pulling you out now. To an outside observer, you never actually cross this line. They'd see you slow down, dim, stretch out like taffy, and fade into redshift until you disappear completely. But from your point of view, everything continues smoothly. It's business as usual, except now the business is gravity, and it's coming for everything you're in the land beyond reach. And nothing, no particle, no signal, no SpaceX-themed prayer will make it back out. Welcome to the place where the universe draws the curtain and ends the act. Because past this point, space-time isn't just curved, it's a funnel with no bottom. The phrase event horizon was coined by physicist Wolfgang Rindler in the 1950s, and it stuck, probably because cosmic nope line was taken. It's not a surface, really. Not like the crust of a planet or the hull of a ship. You couldn't land on it. You couldn't stand on it. It's just the last edge where cause and effect, as we know them, still pretend to have a contract. And here's where things get a bit spooky. If something crosses the event horizon, and you're watching from far away, that thing never quite disappears. Its light takes longer and longer to reach you, red shifting until it fades from visibility, but it always seems to hover at the edge, not falling, not surviving, just ghosting. Some physicists call this the frozen star illusion, where time appears to stop at the horizon from an external view. But inside, oh, you're falling hard. The experience inside the event horizon is often misunderstood. People imagine it as some kind of wild, alien environment, but in reality, from your perspective, things are eerily normal, at least for a little while. You don't feel a sudden lurch or see some sci-fi light show. It's only when you try to do something like escape that the horror starts to make itself known. And let's talk about the shape of that horror. In a non-rotating black hole, our good friend, the Schwarzschild type, the singularity is a point. But if the black hole is rotating, and let's face it, most of them are, you've got yourself a Kerr black hole. And that means the singularity is not a point. It's a ring, a spinning curved line of impossible density, which opens the possibility, according to a few theoretical loopholes, that you might not just fall in, you might fall through. More on that delightful possibility later. For now, you're inside the cosmic boundary where space-time is not only distorted, but fully weaponized. The direction you think of as forward now literally points inward. No matter how fast you try to accelerate, you will only get closer to the singularity. It's not a matter of effort. It's the geometry of this reality. It's like trying to run away from your own shadow when your shadow is tattooed onto your bones. Fringe theories and pop sci dreams aside, here's the sobering truth. There's no known mechanism in modern physics that allows for escape once you've crossed the horizon. No warp drive, no photon tether, no cosmic cheat code. The escape velocity here exceeds the speed of light, and since light is the universe's absolute speed limit, your chances of leaving are, let's say, mathematically rude. Still, the idea of crossing this point fascinates physicists. Some argue that you could extend space-time across the horizon with clever coordinate transformations. In fact, the Kruskal-Seeker's coordinates allow you to chart a smooth map through the event horizon without any physical singularity at the boundary. But that's just math doing cartwheels. reality still says no re-entry. What's more unnerving is what isn't here. There's no debris, no clutter, no noise. Everything that's fallen in, stars, gas clouds, dreams of interstellar vacation homes, it's all gone. Absorbed, shattered, rewritten. And you too are now a data point falling inward toward that gravitational record keeper we call the singularity. Of course, there's the little matter of information. In the 1970s, Stephen Hawking realized that black holes do emit something, Hawking radiation, tiny particles flickering into existence near the event horizon thanks to quantum effects. This led to a big problem. If a black hole evaporates over time, where does the information about everything it swallowed go? Quantum mechanics says information can't be destroyed. General relativity says the singularity eats it for lunch. The two are still not speaking to each other. This is the black hole information paradox, and it's one of the biggest unresolved debates in theoretical physics. Some physicists think the information is smeared across the event horizon, preserved somehow on its surface like a hologram. Others believe it's encoded in Hawking radiation, and a few renegades suggest that black holes might open into other universes, carrying information along for the ride. Historians still argue whether this paradox is a symptom of bad math or a hint at a deeper, undiscovered law of nature. But you're not worried about paradoxes. You're too busy becoming part of one. From here on, every step, every heartbeat, every vibrating particle of you is being recorded by gravity in the most intense diary the universe has ever kept. Not one photon escapes. Not one quark calls in sick. You are archived forever, or at least until the black hole evaporates, which, fun fact, takes longer than the age of the universe. Supermassive black holes could take 10 to the power of 100 years to fade. That's a 1 with 100 zeros after it. Longer than long, more than forever. So unless you're packing a very patient time machine, you're here for a while, so go ahead, scream if you want. The sound won't escape, and besides, even your scream has mass, and gravity's already claimed it. You stretch. Not like a lazy Sunday morning cat-like kind of stretch. No, this is more terminal. You're being spaghettified, which is a real scientific term, blessed by the astrophysics community and everything. It sounds almost adorable, but don't be fooled. Spaghettification is the tidal force equivalent of getting turned into long, limp gravitational linguine. You probably feel it in your ankles first, assuming you had ankles. The gravity pulling on your feet is noticeably stronger than the gravity pulling on your head. The difference is small at first, but the deeper you fall toward the singularity, the stronger it becomes. Eventually, that difference becomes fatal. Imagine being pulled so hard that atoms themselves start to complain. First, molecular bonds snap, then nuclei break apart. And if you're particularly unlucky, gravity even starts messing with the quarks inside your protons and neutrons. This is the most intense tidal stress imaginable. The universe doesn't get more rude than this. And let's be clear, this doesn't happen at the same place for every black hole. A stellar mass black hole, like one that forms when a single massive star collapses, would spaghettify you well before you reach the singularity. You'd be turned into a gravity noodle even before crossing the event horizon. But fall into a supermassive black hole, the kind lounging at the centre of a galaxy, sipping crushed stars through a straw, and you might pass the event horizon in one piece. You wouldn't even feel the stretching at first. So yes, there are different kinds of terrible. Spaghettification, or tidal stretching, is just one symptom of the profound weirdness happening inside a black hole. Remember, gravity isn't a force in the traditional sense. It's the curvature of space-time. When that curvature gets extreme enough, it stops being a nice dip and starts becoming a vortex. You're not falling through space. You are the space being folded in historically. The idea of this kind of gravitational violence wasn't widely accepted. In fact, Einstein himself didn't believe singularities were physically real. He thought they were just mathematical artifacts, bugs in the system. Historians still argue whether his resistance was philosophical or scientific. Maybe he just couldn't accept that nature would be so untidy, that there could be places where his own equations fell apart. but nature is untidy, especially here. Let's shift perspective for a moment. Imagine you're made not of squishy human bits, but of data, strings of information, bits, qubits, whatever the current theoretical flavor is. As you fall, your information is being absorbed, recorded in the gravitational field. This leads to the idea that everything falling into a black hole might somehow be preserved, not as matter, but as encoded information on the event horizon, like the world's darkest USB stick. This is the core of the holographic principle, a bold suggestion that all the information in a volume of space can be described by data on the boundary of that space. It's like being able to describe everything inside your house using just the paint on the outside walls. Wild! Absolutely. But there's some math to support it, and in black holes, that math gets especially persuasive. Back inside your fall, things are feeling less physical. You're no longer a falling body, you're an infalling observer, a term physicists use to describe something experiencing space-time from inside the event horizon. Your mass is irrelevant now, your dimensions are irrelevant. You're no longer navigating reality, you're being redefined by it, and you're not alone. The singularity may be invisible, but it's crowded with everything that's ever fallen into this black hole. A cosmic junk drawer of stars, light, theories, possibly even civilizations. There's a rather fringe theory that advanced alien civilizations might hide information in black holes because, well, where else would you store your secrets if you don't want them found? Historians scoff at this, but still, if you were looking for the ultimate encryption system, nothing beats literally can't escape. Now, here's where it gets more unsettling. As your body, or what's left of it, continues to stretch, your experience of time becomes warped beyond recognition. You might feel as if you're slowing down, like a tape gradually being dragged through syrup. Seconds feel like hours, then centuries, then nothing. Not because time stops, but because it becomes meaningless. Physicists often model this process with Penrose diagrams, little two-dimensional maps of space-time that help track how light and matter move in extreme conditions. In these diagrams, your path doesn't just end, it terminates at a singularity line. That's the equivalent of a cosmic full stop, a literal dead end in the architecture of the universe. But here's a fringe nugget to chew on while you're being converted into gravitational linguine. Some researchers think spaghettification might be survivable in theory. Maybe. If you fall feet first into a rotating black hole and thread the needle through the ring singularity, some exotic physics might allow you to pass through without being destroyed. You might even emerge somewhere else. Where? Good question. The answers range from another universe to a different point in space-time to a very awkward dinner party hosted by parallel versions of yourself. But again, that's deep into speculative territory. Think of it as the interstellar version of hoping your toast lands butter side up. Still, the concept of geodesics, the paths objects follow through curved space-time, suggests that, technically, you can fall through the singularity along certain trajectories. Whether or not your atoms survive the journey is, let's say, a secondary concern. So, let's recap. While you still have a few distinguishable molecules, you fell into a black hole past the event horizon and began stretching due to tidal forces. If it's a stellar mass black hole, you're toast. No further reading required. But if it's a supermassive one, you're experiencing an eerie calm stretch, slipping through gravity's fingers like spaghetti through a strainer. You might be encoded on the surface. You might be preserved in Hawking radiation. You might be headed for another dimension, or you might just be disassembled permanently in a place where math waves a white flag. And all of this, the stretching, the squishing, the disappearing, isn't science fiction. It's just gravity. Doing what gravity does best when left alone with too much mass and not enough chill. You're not quite you anymore, not in the usual sense. Your body, your atoms, your quarks, long surrendered. Even your timeline has gone rogue. You're a thought, a trajectory, a math problem screaming through space-time's final basement. And this is it, the singularity, where space and time no longer make sense, where gravity doesn't just bend the rules, it melts the rulebook and eats the ashes. If the event horizon was a point of no return, The singularity is a point of no definition. You've crossed from weird physics into full-blown undefined behaviour. The universe has thrown up its hands and gone, I don't know man, good luck. At the singularity, density becomes infinite, not really big, not off the charts. Infinite. A single point, zero volume, into which all the mass of everything that's fallen in has collapsed. It's a contradiction, and that's the problem. Because if you put 0 in the denominator and all of mass in the numerator, even your calculator gives you side-eye. You've officially arrived at where math breaks down. Now, you might be wondering, wait, infinite density? Doesn't that mean literally everything is squished into nothing? Correct. Well, kind of. See, nobody really knows what a singularity actually is. In physics, it's what we call a mathematical singularity, a point where our equations return infinity or undefined, which is not how physics is supposed to work. Imagine asking for directions and someone hands you a blank map with a note that just says don't. Einstein's general relativity is the thing that predicts singularities, and yet it also fails to describe them. That's not a contradiction. It's just the universe being hilariously rude. General relativity gets you to the edge, points into the darkness, and then bails, and quantum mechanics. It doesn't even try to walk through the door. The two great pillars of modern physics, relativity and quantum mechanics, do not play nice here. At the singularity, they speak entirely different languages. Relativity talks smooth curves and gravitational wells. Quantum physics is over in the corner, yelling about probabilities and uncertainty and particles that are also waves unless observed after a latte. Some physicists believe that at the centre of a black hole, quantum gravity should take over. A long theorised, never yet observed unification of the big and the small. That magical theory we don't have yet. The one that would bridge general relativity and quantum mechanics. We've been searching for it under many names. String theory, loop quantum gravity, maybe even holography. Historians still argue whether Einstein, toward the end of his life, suspected that black holes would reveal this missing piece, or whether he thought they were just signs that the current physics wasn't complete. Either way, the singularity is a blinking neon sign that says upgrade required. So what could the singularity actually be? Some suggest it's not a point at all. Not in the physical sense, it's just where our current understanding halts. Others suggest that Planck scale physics, that is, at scales smaller than 10 to the negative 35th meters, introduces fuzziness that prevents infinite density. In these models, space and time are quantized, like pixels on a cosmic screen. The singularity might just be a region of extremely curved but still finite geometry. There's also an idea called cosmic censorship, proposed by physicist Roger Penrose. It's a comforting little hypothesis that says all singularities are hidden behind event horizons. That is, nature censors these horrors from the rest of the universe. No naked singularities, no physics flashing the neighbours. But we don't know if cosmic censorship holds up in every case. There are hypothetical solutions to Einstein's equations, Kerr and Reissner-Nordström black holes, that suggest rotating or charged black holes could expose their singularities under the right or wrong conditions. And that leads to all sorts of delicious instability. For now, though, you're inside a safe singularity. Safe as in completely unknowable and fatal. Let's get weird for a moment. You've probably heard that space and time are interchangeable inside a black hole. And that's sort of true. The radial coordinate, the direction you fall toward the singularity, becomes time-like, meaning that going deeper into the black hole isn't just a direction, it's a when. You're not moving through space toward a place. You're moving through time toward a moment, and that moment is the singularity. You can't stop. Not because you're moving fast, but because not falling inward would be like trying to stop time. You can no more prevent your arrival at the singularity than you can prevent next Tuesday. For you, the singularity isn't a location, it's your future, and that's kind of beautiful, unless of course time ends there, and there's an actual physical boundary where everything stops: your existence, your coordinates, your particles, your probabilities. No more past, no more future, just a finality that isn't in time but outside it, a death not of matter, but of causality itself. Or maybe the singularity isn't the end. Some physicists imagine it's a transition, like a tunnel or a bridge, a place where space collapses inward so tightly that it re-expands on the other side. This leads to the tantalizing idea that black holes could be gateways to other universes, that every singularity is the Big Bang of somewhere else. This is called the baby universe hypothesis, and we'll explore it more soon. But just imagine, every time a star dies, it creates not just a singularity, but a whole new cosmos, bubbling off from our own. A cascade of realities, each born from the crushed leftovers of the last. Sound far-fetched? Definitely. But compared to infinite density at zero volume, it starts to feel downright reasonable. Fringe fact of the night. Some 1960s physicists, notably John Wheeler, toyed with the idea that entire particles could be tiny black holes, that an electron, for example, might be a mini singularity. The math didn't pan out, but the imagination was there. The idea that matter itself could hide little rips in space-time. Well, it's still a vibe, so here you are. Not falling, not flying. You're being rewritten by a place that may not exist. You've entered a coordinate on the map of physics that simply says, here, dragons eat the equations. If someone could freeze this moment, record what happens to you right now, they would have a better shot at understanding quantum gravity than any physicist alive. But no one can. Not even light can carry that information outward. You're alone and unknowable and eternal, in the most temporary, transient way imaginable. It's not just that science hasn't figured this out, it's that science is still arguing about whether this is even real. If the singularity is where general relativity gives up, then this is where quantum mechanics tries to sneak. In through the side door, nervously holding a cup of theoretical coffee and muttering something about uncertainty. And leading this awkward intervention is none other than Stephen Hawking. The man who dared to ask what happens when the cold logic of black holes meets the twitchy chaos of quantum particles. You're already at the core now, swirling in a region that defies space and time. But even here, something quantum is happening. Something subtle, tiny, flickering sparks along the edge of everything. Not enough to stop the fall, but just enough to complicate the story. See, black holes were once thought to be perfect absorbers. Everything went in. Nothing came out. Not even information. They were the universe's ultimate delete button. Then along came Hawking in the 1970s, side-eyeing the whole concept and asking, but what if quantum fields near the event horizon got a little twitchy? According to Hawking, the vacuum of space isn't really empty. It's full of quantum fluctuations, tiny particles and antiparticles popping into existence in pairs, like cosmic flash mobs, then annihilating each other just as quickly. But near the event horizon, one of these particles might fall into the black hole while the other escapes. The result? The black hole loses a tiny bit of mass, and that's Hawking radiation, a ghostly, nearly impossible to detect glow emitted by black holes. Not because something is escaping from inside, but because the event horizon itself is bleeding mass through quantum mechanics. Over enough time, trillions upon trillions of years, a black hole could evaporate. Poof. Gone. Just a whisper of heat left behind. And that whisper, it changed everything. Because it meant black holes weren't perfectly black after all. This revelation launched a storm of debate. If black holes evaporate, what happens to all the information about what fell in? Quantum mechanics insists that information can't be destroyed. Ever. Not even by a black hole. But general relativity is just like, LOL, bye. So began the infamous black hole information paradox. Are you starting to feel like you've been recruited into a decades-long physics brawl? You have. Welcome. It's extremely exclusive. The dress code is mostly existential dread physicists around the world scramble to explain how information might be preserved. Some suggested that it gets stored in the event horizon itself, encoded in a kind of 2D hologram. Others said it escapes in the Hawking radiation, just incredibly scrambled. And some took it further, proposing that information is never really inside the black hole to begin with. It just gets entangled across the horizon in weird quantum ways. Hawking himself wasn't sure. He famously flip-flopped over the years. For a while, he said information was lost. Then he said it wasn't in 2004. He made headlines announcing he'd solved the paradox, claiming that black holes do not destroy information after all, but his answer was vague and still heavily debated. Historians still argue whether that announcement was more of a media moment than a resolution. Some say he was right but incomplete. Others think the paradox remains unsolved. Either way, it made one thing clear. If we want to understand black holes, quantum mechanics has to be part of the picture. And this brings us to the great hope of modern theoretical physics, the search for a quantum theory of gravity. We have the rules of the very big, Einstein's relativity, and the rules of the very small, quantum mechanics. But we don't have one theory that describes both at the same time. Black holes? They demand it. They are the perfect arena where gravity and quantum effects collide, grind their teeth, and mutter angrily about equations. One popular attempt at this fusion is string theory. In it, particles are not points, but tiny, vibrating strings, each frequency corresponding to a different particle. It offers the tantalizing possibility of unifying all forces, including gravity, into a single framework. In some versions of string theory, black holes are not singularities at all, but tangled webs of branes and strings, pulsating at the Planck scale. Another contender? Loop quantum gravity, which takes a more conservative route. It proposes that space itself is made of tiny loops, woven into a fine fabric that quantizes space-time. In this model, the singularity might not be a point of infinite density, but a bounce, a place where matter collapses to a minimum volume and then rebounds cosmic trampoline vibes. And yet, none of these theories have been proven. They're playgrounds of math, speculation, and elegance, but no experiments have confirmed them, not yet. Still, the presence of Hawking radiation tells us that something quantum is happening at the horizon, something that might hold the key to solving not just black holes, but the origin of the universe itself. And there's one more twist. Recently, physicists have been exploring the idea that the entanglement of particles, one of the core features of quantum mechanics, might literally build space-time. That is, space as we know it might emerge from patterns of quantum entanglement. In this view, a black hole tearing that entanglement apart could be tearing at the fabric of reality itself. You've been falling all this time, piece by piece, concept by concept. But now, you're not just a victim of gravity. You're part of a cosmic experiment, a crucible in which the laws of physics are being melted down and recast. You are, quite literally, where the answers are, or at least where the questions get sharper. And maybe, just maybe, Hawking's quiet whisper of radiation is the universe's way of sending messages from the place where math dies, time folds, and nothing should escape. A slow, shimmering leak from the edge of forever. You've heard of burning questions. Now meet a burning horizon, or maybe not, because just when? You thought things couldn't get stranger than spaghettification and Hawking radiation? Physicists decided to fight about whether you'd be incinerated the moment you crossed the event horizon. That's right. You might not fall gently into a black hole at all. You might smack into a wall of quantum flame known as the firewall. No, not like the cybersecurity kind. This firewall doesn't protect your files, it tortures your atoms. Here's the problem. Hawking radiation, it's back. Again. Remember, Hawking said black holes emit radiation due to quantum effects near the event horizon. This implies that over time the black hole loses mass, and potentially evaporates completely. Fine, that's already mind-bending. But in 2012, a group of physicists including Almheri, Marolf, Polchinski and Sully, collectively called AMPS, dropped a theoretical grenade into the discussion. Their logic went like this. If information is preserved, and if Hawking radiation carries that information out of the black hole, like little encrypted leaks, then the particles near the event horizon must be entangled with particles far away in the emitted radiation. But there's a catch. Quantum mechanics has a rule. A particle can't be fully entangled with two separate things at once. That's like trying to be married to two people who don't know about each other and still expect the universe to support your choices. So if Hawking radiation is entangled with far-off particles, it can't also be entangled with stuff just inside the event horizon. This messes up the tidy vacuum of space near the black hole's surface, and, according to the math, results in a very unpleasant solution. A firewall, a literal quantum wall of high-energy particles. Think gamma-ray blast furnace that incinerates anything trying to pass through. So congratulations, according to this logic, you don't get to fall quietly into the abyss anymore. You get flash-fried at the threshold. Suddenly that graceful descent into a singularity is replaced by a cosmic barbecue, but not everyone's buying it. Some physicists argue that firewalls break a much more cherished principle, the equivalence principle. That's the idea that falling into a gravitational field should feel just like floating in space, at least locally. For you, an infalling observer, there should be no drama at the event horizon, no fire, no screams, just a quiet glide. This principle is one of the cornerstones of general relativity. If it breaks, relativity breaks with it, and Einstein is going to need a lie down. So what gives? Well, there are a few competing theories trying to dodge the firewall bullet. One, complementarity. This one's a bit of quantum PR spin. It says both stories are true, depending on your perspective. An outside observer sees the firewall, an infalling one doesn't. Kind of like how light can be a wave or a particle depending on how you look at it. But that starts to sound suspiciously like cheating. ER equals EPR minus. This is a wild one. Proposed by Leonard Susskind and Juan Maldacena, it links two of the weirdest ideas in physics: Einstein-Rosen bridges, wormholes, and Einstein-Podolsky-Rosen entanglement. In short, it suggests that entangled particles are connected by tiny wormholes, and maybe, just maybe, the particles near the event horizon aren't violating entanglement rules at all. They're just using space-time shortcuts we haven't understood yet. This theory might allow Hawking radiation to carry information without causing firewalls. Fuzzballs. No, not tribbles. This one comes from string theory, and it suggests that black holes don't have a smooth horizon at all. Instead, what we think of as a black hole is really a tangled, stringy mass, a fuzzball, with no true singularity inside. If that's true, then there's no place for a firewall to be, and nothing ever falls through a traditional horizon. You just land in the fuzz, which sounds better than fire, depending on your tolerance for cosmic ambiguity. Historians still argue whether the firewall proposal is a fatal blow to our current models, or just another sign that we're missing a deeper principle. But the controversy itself is oddly comforting, like finding out even the brightest minds in the universe are still saying, "Wait, what?" at least once a week. For you, the theoretical test subject plummeting into the singularity, it all depends on which physicist you ask. In one version of reality, you're already vaporized. In another, you're floating peacefully inside the event horizon. In a third, you're tangled in a ball of quantum spaghetti, half dead, half data. And here's the cheekiest part. No one can check. The firewall paradox, like most black hole dilemmas, is fundamentally untestable. No experiment, at least with current technology, can drop someone into a black hole and report back. It's the ultimate theoretical playground, fenced off with infinite gravity and laced with quantum landmines. Some physicists think that means the question isn't worth asking until we have better tools. Others argue that black holes are precisely where we need to push our theories to the edge, because only here do we get the extreme conditions where both relativity and quantum mechanics must collide. You, of course, are busy either becoming a charcoal smear on the firewall or passing quietly into the core of the singularity, depending on the math. But whichever version is true, one thing remains certain: something has to give. We can't keep both Hawking radiation and smooth horizons and unbroken quantum entanglement. Without contradictions, one of our cherished assumptions has to fall, and black holes, ever the drama queens, are forcing us to choose. Either general relativity is incomplete, quantum mechanics needs rethinking, or the universe has a horrifyingly literal burn filter at the edge of every black hole. Pick your fighter. Meanwhile, you're still falling, or you were, or you will be, in some frame of reference that no longer agrees with yours. Outside the black hole, an observer sees your image fading, stretching, slowing. But inside, whether you glide or ignite, you've now passed the point where cause and effect have anything nice to say to each other. and the singularity is still waiting. Okay, so you've made it through the firewall, or avoided it, or didn't believe in it to begin with. Honestly, it depends on which flavour of physics you subscribe to on your way down, but let's be optimistic and assume you weren't deep-fried at the horizon. You're still falling, still stretching, and still stubbornly existing in whatever quantum glitched form existence now takes. But now, let's look for a way out, or sideways, or elsewhere. Because once you've survived entry into a black hole, and yes, survived, is doing some very heavy lifting here, you may begin to ask the most heretical, wonderful question of all. Can you get out again? Not the way you came, of course. That door is closed. But maybe, just maybe, there's another one. And this is where theoretical physics, tired of pretending it's sensible, throws open the wormhole cabinet and invites you to imagine, what if singularities aren't dead ends? What if they're portals? Welcome to the dazzling and very hypothetical world of wormholes, white holes, and other cosmic escape routes that are equal parts genius and nonsense. Buckle up. You won't be returning through the same space-time you entered from. Let's start with the classic, the Einstein-Rosen bridge. Back in 1935, Albert Einstein and his colleague Nathan Rosen tried to solve the problem of singularities by linking two sheets of space-time via a bridge. A shortcut. On paper, it connected two black holes through a tunnel-like structure. The result? A wormhole. A theoretical passage through space-time that could, in theory, allow you to enter one side and exit somewhere else, maybe light years away, or in another universe entirely. But there's a catch. There's always a catch. The original Einstein-Rosen bridge isn't traversable. It collapses before anything can pass through. Like a bridge that disintegrates as soon as you set foot on it. Sad. Still, later physicists, Morris and Thorne among others, wondered, could a wormhole be propped open with just the right ingredients? Perhaps some exotic matter, stuff with negative energy density, could stabilize it. Think of it like scaffolding made from anti-gravity duct tape. And if you could stabilize a wormhole, you might do more than just escape a black hole. You might travel through time, no big deal. Now let's pivot to something even stranger. White holes. If a black hole is a region of space-time from which nothing can escape, then a white hole is the opposite, a region into which nothing can enter. Only stuff comes out. It's like a cosmic sneeze. Matter and energy are ejected, but nothing ever falls in. White holes were first proposed as mathematical inverses of black holes. You run the equations backward and voila, instant theoretical expulsion chamber. But unlike black holes, we've never seen a white hole. No signals, no candidates, just equations that allow them to exist, in theory, like reverse shadows we've never caught in the act. Yet some physicists suggest they might be connected, that every black hole might be linked, across some dimensional fold, to a white hole in another part of the universe, or another universe entirely. The matter that falls into the singularity doesn't just get crushed, it tunnels through, transformed, and is spat out in some other realm. This gives rise to the black hole-white hole bridge hypothesis. The idea is delicious. You fall in, crushed by tidal forces, distorted by gravity, and somehow re-emerge in a bright eruption of energy somewhere else, the Big Bang itself, according to some fringe. Theories could have been the other end of a black hole in a parent universe. Our universe, the baby, the ultimate wormhole exit. Historians still argue whether early cosmological models that hinted at time reversal symmetry were unknowingly describing white holes. It's unclear whether white holes are physically plausible or just mathematical curiosities that happen to exist in our equations when we press the reverse button. And if that weren't wild enough, there's another escape route you've probably seen in fiction. Rotating black holes, aka Kerr black holes, may contain something even weirder than a singularity. If you were to fall into one along a precise trajectory, and let's admit you probably already missed it, you might avoid the singularity entirely and pass through a ring of extreme density into a new space-time region. The math here gets spicy. Some versions predict wormholes, others suggest closed time-like curves, i.e., loops in time. Yes, time travel. You fall in, and instead of dying, you emerge earlier or later, or sideways, in someone else's Tuesday. But again, huge caveat, These solutions often rely on idealized, perfectly symmetrical black holes. No dust, no radiation, no cosmic noise. In other words, not the kind you'd ever actually find in reality. Still, they tempt the imagination. What if, in the final moment before you're annihilated, your information tunnels through a Planck-sized throat and births a new region of space-time? What if every black hole is a kind of cosmic seed, and singularities are really just transition points, like the husk of a sprouting dimension? If that's true, then you are part of a voyage, not into death, but into transformation. Your particles may not survive, but your data, your energy, your essence, if we can indulge a poetic term, might be reconfigured into the structure of something new, a star in another galaxy, a law in a newborn universe, a flicker in someone else's sky. Even the more grounded physicists, those who roll their eyes at white holes and wormhole adventures, admit that we don't yet know what happens at the singularity. So long as general relativity and quantum mechanics are incompatible, this zone remains the blankest part of the map. A place for thought experiments, paradoxes, and yes, dreams. And maybe that's the whole point. Black holes aren't just objects, they're tests, not just for matter, but for understanding, for the limits of physics, logic, and imagination. A reminder that the universe isn't done surprising us, and might never be. So you keep falling, or tunneling, or escaping, or becoming. Whatever happens beyond the singularity, you've crossed into the space where questions outnumber answers, and where even the most grounded minds must admit, we might have no idea what reality actually allows, and sometimes that's the best place to be. You've fallen so far in so many theoretical directions that by now even your questions are starting to blur. You've been spaghettified, incinerated, fuzzballed, possibly quantum entangled with your own memory of falling. But just when you thought you'd reached the bottom of the black hole's bag of tricks, something even stranger emerges from the swirl of equations and thought experiments. What if this whole thing, this singularity you've plunged into, isn't the end? What if it's a beginning? Hold that thought. Let's back up. Not physically, you're still falling, but conceptually imagine a star collapsing under its own gravity. A truly massive one, bigger than anything our sun could dream of being. After it runs out of fuel, fusion stops, and the internal pressure can no longer resist gravity. The core collapses inward, fast, relentlessly. And according to the math, if it's massive enough, the collapse doesn't stop at neutron star. It doesn't pause at quark soup, it keeps going, all the way to a singularity. But here's the thing, that same mathematical path, that same compression down to zero volume shows up elsewhere, at the beginning of the universe, our universe, the Big Bang. In fact, if you take the equations of general relativity and run them backward, rewind the cosmic film reel, you find the expanding universe shrinking down, smaller, denser, hotter, until it too hits a singularity, a point of infinite density, zero volume, the ultimate once upon a time. Historians still argue whether the Big Bang was truly a singularity or just the farthest back we can meaningfully talk about. But the resemblance is uncanny, a universe born in a flash from a point we can't describe, and now here you are, deep inside another such point. What if the two aren't just similar? What if they're linked? Enter the baby universe hypothesis. According to this idea, when a black hole forms, it doesn't just destroy what it consumes, it hides it, tunnels it, maybe even births an entirely new universe inside, completely disconnected from our own, unreachable across the event horizon. From our side, everything falls in. From the inside of that new universe, it's an entirely separate Big Bang. That's right, the singularity you're spiraling into could be the Big Bang of another cosmos. You're not falling to the end of this universe, you're becoming the foundation of another one. In this model, each black hole seeds a new realm, maybe one with different physical constants, maybe one where time ticks in reverse, maybe one where toast always lands butter side up, or one eerily like our own, just a little off around the corners. Some theories from quantum cosmology support this. In particular, physicist Lee Smolin proposed a controversial but intriguing idea: cosmological natural selection. In this view, Universes that produce lots of black holes generate more baby universes. Over time, the population of universes selects for properties that make black hole formation more likely. Yes, you heard that right. It's Darwinian evolution for universes. You might be inside a kind of cosmic evolutionary tree, a branch sprouting from an older parent universe with your black hole Singularity as its root system. If this sounds suspiciously like science fiction, you're not wrong. But the math isn't laughing, it's cautiously curious. In some models, the transition from one universe to the next avoids the infinite density problem by replacing the singularity with a bounce. As matter compresses under gravity, quantum effects push back, eventually causing a rebound, a bounce that launches a new universe outward. This idea, known as a quantum bounce, is one possible feature of a loop quantum gravity. It replaces singularities with transition zones, from collapse to expansion, and this has serious implications. It means that black holes don't end anything, they just convert one space-time into another. So what would that mean for you? Well, it's complicated. Let's assume your consciousness hasn't already been stretched across a dozen dimensions and left for dead. Let's say some part of you, maybe your information, maybe your subatomic residue, is now present at the seed of a new universe. You might experience a fresh beginning, not with memories but with presence. Maybe you are the first fluctuation in that newborn space-time. A tremble in the quantum foam that will one day become a star, or a particle, or, dare we dream, a sleep-deprived cosmic narrator. And here's a fringe fact to keep you warm inside your quantum rebirth. Some physicists propose that our own universe might have emerged from the collapse of a black hole in a higher dimensional space. That what we see as the Big Bang is actually a white hole spewing matter into a fresh timeline, our timeline. In that sense, black holes could be both death and birth portals of passage between realities, engines of cosmic recycling, or maybe not. Maybe it's all poetic nonsense dressed in tensor calculus, but the resemblance between the start of our universe and the structure of a singularity is hard to ignore. Both are regions where physics as we know it stops being helpful. Both are bound by extreme density, curved space-time and theoretical hand-waving, and both leave behind mysteries we're still clawing at with telescopes and chalkboards. And who knows? Maybe this cosmic recursion is infinite. Maybe every universe gives rise to more black holes, which birth more universes, which birth more black holes, like a nested set of gravitational Russian dolls. The multiverse, not as parallel threads, but as generational chains, with ancestry written in collapsed stars. If so, your journey isn't tragic. It's generative. You're not being erased, you're being repurposed, upcycled into a brand new space-time event. You, and everything that ever fell in with you, are the spark for an entire cosmos, one that may last billions of years, expand, cool, and wonder where it came from. It came from you, or from what you used to be. You're deep now, past metaphors, past equations, past the point where most thought experiments even bother to keep their shoes on. You're inside the most extreme object the universe allows, the black hole. But more than that, you're face to face with its ultimate tantrum, gravity pushed to its breaking point. Forget stretch and squeeze. That was spaghettification. Forget Hawking radiation and bouncing baby universes. Those were theories. This is the real endgame. What happens when gravity throws a fit so intense, so focused, that space-time itself breaks under the pressure? Let's start with the obvious. Gravity loves company. It holds galaxies together, keeps moons from wandering off, and glues your feet to the Earth. Most of the time, it's reliable, gentle, persistent, but it's also relentless. Add enough mass, remove the structural support of nuclear forces, and gravity doesn't just collapse matter, it collapses context inside the singularity. Gravity becomes unhinged. You're dealing with a gravitational field of infinite strength, a place where curvature of space-time isn't just steep, it's a vertical wall. In ordinary space, gravity curves space-time subtly. Think of planets tracing graceful orbits along a gently sloping surface. But here, the slope becomes a cliff. Then the cliff folds in on itself and eats your coordinate system for breakfast. There's no up, no down, no before, no after. You've reached the place where Einstein's general relativity turns into interpretive dance. Let's talk about tidal forces one more time. Not the ocean kind, but the cosmic sort. These forces are a result of gravity changing over distance. They're what stretched you like pasta earlier. But near the singularity, the change in gravity between 1 centimetre and the next becomes not just measurable, it becomes catastrophic. The closer you get to the centre, the more violently gravity varies from point to point. It's not pulling you inward as a whole, it's pulling every part of you in different ways with increasing intensity, not just stretching you end to end. It's twisting, squeezing, folding. If there were any remaining atoms to tear apart, this is where they'd say their final goodbyes. And this isn't limited to physical objects. Even light cones, the diagrams that describe what events can influence what other events in relativity, collapse here. Normally, a light cone points forward in time, letting you visualize the future that any particle or observer can affect. But inside a singularity, those cones tilt inward, then shrink, then crumple into nothing. There is no future path, no outside, no after. The curvature of space-time becomes infinite, a phrase that, if we're honest, should come with a health warning. Because in physics, infinite doesn't mean very big, it means our model is sobbing in the bathroom. Infinite curvature means the Ricci scalar, a way of measuring how. Space-time bends is not just large, but undefined. The usual tools, Riemann tensors, geodesic equations, stress-energy metrics, go haywire. If you plot them, they don't just misbehave, they cease to plot. This is gravity's ultimate temper tantrum. Historians still argue whether the singularity represents a real physical location or just a placeholder for where our understanding ends. Some believe it's a true point of infinite density. Others argue it's merely a signpost that says, "Stop! Physics ahead is under construction." Either way, no one has managed to peek inside. Here's a metaphor physicists sometimes use. Imagine space-time as a fabric. Gravity is what causes that fabric to bend. A planet makes a dent, a star makes a bigger one. A black hole, it pokes a hole straight through the sheet, and the singularity, that's the needle breaking off and vanishing into a place no thread can follow. Now, there's something particularly cruel about the singularity. It isn't just a place you end up, it's a place that pulls you into it without choice, and then ends your ability to describe anything. Even if you had a ship made of neutronium piloted by tachyon-boosted AI, it wouldn't matter. The laws of physics don't break after you arrive. They break as you approach. It's the only destination in the universe where approaching it causes reality to decompose in real time. Let's talk units. The Planck length, 1.6 times 10 to the negative 35th meters. The Planck time, 5.4 times 10 to the negative 44th seconds. At these scales, quantum effects dominate, and gravity is expected to undergo a phase shift we still don't understand. And that's probably the scale at which the singularity actually lives. In theory, beyond that point, quantum gravity would take over and save us from infinity. But in practice, we don't know, because our math breaks before we can even test those waters. It's like trying to read the bottom line of an eye chart while being punched in the retina by space-time itself. And here's where it gets even more poetic. Some physicists suspect that inside the singularity, causality may not apply. Cause and effect become tangled. Timelines might reverse. You could, hypothetically, have effects that don't have causes, or loops of causality that feed into themselves endlessly. It's not that time ends, it's that it becomes meaningless. And yet, there's structure here. Maybe not one we can map, but something remains. The singularity is still a solution to Einstein's field equations. It's still there in the math, screaming silently from within the curvature. Let's not forget our old friend Penrose. Roger Penrose proved that under general conditions, a collapsing star must produce a singularity. Not might. Must his singularity theorems don't care about what's inside. They just say, if these conditions hold, then infinite curvature happens. But Penrose also hinted that the singularity isn't the final word. It's just where the current model stops talking. There are other voices trying to whisper through the math. Ideas like asymptotic safety, where gravity's strength levels off at high energies instead of going infinite, or string theory landscapes, where vibrating one-dimensional strings dance instead of particles, and perhaps those strings don't let you crush matter infinitely. Even causal set theory posits that space-time isn't continuous but built of discrete events, tiny nuggets of causality. In such a model, singularities might not be possible at all, because there's no such thing as infinitely close points. But again, we're in speculation territory. What we know is that the singularity is where the best physics we have drops the chalk and walks away. So where does that leave you? Maybe you're smeared across a non-local surface in some higher dimensional geometry. Maybe you're a set of collapsed coordinates in a tensor field with no future light cone. Maybe you're the blueprint for a new universe, or the last shudder of this one. But one thing is certain, you are now part of gravity's ultimate expression, not as a passenger, not as an object, but as a contribution to a question no one has answered. You haven't just fallen into a singularity, you've fallen into the unfinished sentence of the cosmos. The singularity doesn't speak, but somehow it says everything. You're not falling anymore. There's no direction left to fall in. You're not in motion because motion requires space and time, and those have both curled up, handed in their resignation letters, and politely exited the building. What's left is, well, we don't have a word for it. Even nothing implies too much. This is post-nothing. This is the backstage of reality, where the lights are off and no one ever scheduled cleanup. So naturally it's time to ask the question, what happens to time at the centre of forever? From the outside, time around a black hole behaves oddly but predictably. The closer you are to the event horizon, the more time slows down relative to someone far away. This is time dilation, thanks to general relativity. It's been experimentally confirmed satellites experience slightly different rates of time than people on Earth's surface. That's why your GPS has to adjust for relativity every time it tells you where to get tacos. But near a black hole, this time, distortion becomes extreme. Stand too close to the event horizon, and the entire history of the universe might flash by while you check your watch. And if you cross that boundary, you're still moving forward in time, your time, but now, forward points toward the singularity. Here's the twist. The singularity isn't just a place in space, it's a moment in time. In a non-rotating, Schwarzschild black hole, the coordinate we call radius becomes time-like once you pass the event horizon. That means moving inward isn't optional, it's mandatory. It's as inevitable as next Tuesday. And the singularity, that's your future. You can no more avoid it than you can avoid aging. Historians of science often note how revolutionary this is. It flips the whole idea of space and time inside out. The place you're falling into isn't there, it's then. And if that doesn't make your eyebrows try to jump off your face, you're probably already quantum foam. So what does time mean at the singularity? Let's say somehow you could remain coherent at that point. No stretching, no shredding, no firewalling. Just you, floating in the moment where time collapses. You'd find that your ability to define before and after breaks, not just because clocks don't work, because there's no meaningful way to tell the order of events. The causal structure, the network of what causes what, disintegrates. Every direction is inward. Every moment is now. And weirdly, some theoretical frameworks suggest that this moment might be infinitely short and infinitely long, at the same time infinitely short, because in your frame, you're crushed to a point in 0 seconds. Infinitely long, because from the outside, where time stretches to infinity as you approach, the singularity is something you never quite reach. You're suspended in a paradox, always arriving, never arriving, and both are true, depending on which clock you trust. A fun twist? Some cosmologists propose that time itself emerges from the relationships between quantum systems. That is, time isn't a fundamental thing, it's something we construct from how particles relate to one another. If that's true, then when those relationships break down, like, say, in a singularity, so does time. No particles, no frames, no clocks, no time. In this view, the singularity isn't just a place where time ends, it's where time ceases to be meaningful. You could say time is frozen, but even that metaphor gives it too much credit. It's not stopped like a paused video, it's deleted like the idea of colour when there's no light. Now let's peek at the idea of closed time-like curves. These are hypothetical loops in space-time that allow for time travel, like taking a walk and ending up exactly when you started. Some rotating black hole solutions, like Kerr black holes, allow for these loops in their math. And if these structures are real, a big if, it could mean time inside a black hole isn't linear, it could loop. It could fold. You could exist in a kind of eternal moment, cycling endlessly through the same instant, not even aware that you've been here before because there's no before to compare it to. Of course, the real kicker is this. We have no observational evidence of any of this. None. Everything we've said about time at the singularity is based on extrapolations from theory, stitched together with educated guesses and cosmic duct tape. Even the best equations become meaningless at infinite curvature. And yet, some physicists cling to hope. They think quantum gravity, that elusive unification of general relativity and quantum mechanics, will rescue time from oblivion. In some versions of this dream, the singularity isn't infinite. It's just very, very small, compact but describable, crunchy but not nonsensical. Loop quantum gravity, for instance, replaces the continuous fabric of space-time with discrete units, tiny loops of space and time that make up a granular structure. In this model, the singularity doesn't crush everything into a point. Instead, it transitions, it bounces. Collapsing matter reaches a minimum volume, then expands again. Time, rather than ending, gets redefined. That bounce? It could mark the start of a new universe, a new arrow of time. And perhaps that arrow points away from the singularity, in a new direction, in a new space-time, in a reality that looks suspiciously like our own. If so, time didn't die in the singularity, it just changed its course. Here's a quirky historical tidbit to tuck under your pillow. In the late 1700s, long before Einstein or quantum mechanics, the French mathematician Pierre-Simon Laplace speculated that there might be stars so massive, not even light could escape them. He had no concept of space-time or singularities, but his intuition poked at the same mystery, places where time and space might go weird. Today, we've come full circle, from spooky stars to space-time implosions to the idea that time, as a concept, might only exist when it has somewhere to go. And in here, in the singularity, it doesn't. So maybe the last beat of time is a whisper, or maybe it's a branching, a divergence, a sigh before a universe exhales into being. Because if time began once, from a singularity, who's to say it won't begin again? You hover. Well, not hover exactly. There's no space to suspend you, no time to keep you in motion, no frame of reference left to define here or now. But let's say you're still present in some form. At the end of a gravitational journey that wasn't really about movement, but about transformation. So where are we? Let's tug on the only thread that still makes sense, the connection between this singularity, dark, inward, consuming, and the one we all came from, the Big Bang. It's almost poetic. Your fall into a black hole with all its shredding, squeezing, and quantum bickering ends in the same kind of singularity that supposedly birthed space, time, and the stars themselves. A symmetry so absurdly elegant it feels intentional. Of course, that makes people nervous. Because the Big Bang wasn't just a bright flash at the start of time, it was a singularity too. A place where all matter and energy, all space-time itself, was packed into an infinitely dense point. Sound familiar? Some physicists see this similarity and get a little spark in their eye. Maybe these aren't just two versions of the same math trick. Maybe they're two sides of the same cosmic coin. There's a branch of cosmology that leans into this idea. We touched on it in your last freefall, but now we're going deeper, the bouncing universe theory. In this view, the universe doesn't begin and end. It cycles, it collapses, then rebounds. Each black hole isn't a termination point, but a starting point for a new Big Bang, an expanding cosmos growing inside the compressed heart of another, a black hole here. A Big Bang there. Your fall, then, isn't into nothing, but into potential. Let's go deeper still. In some versions of loop quantum cosmology, singularities don't really exist. Quantum effects smear them out. You never reach infinite density. Instead, you reach a minimum volume, a point where the pressure is so extreme that space-time undergoes a kind of quantum bounce, and in that bounce, a new universe is born. In that model, the Big Bang wasn't the beginning, it was just the most recent rebirth, which means our universe might carry the imprints, the wrinkles, the echoes of what came before. And here's where it gets even weirder. Some cosmologists have suggested that black holes in our universe could be connected to the origins of others, that the collapse of a star here becomes the Big Bang of a universe there. Not a neat tunneled wormhole, but a one-way transition, like a birth. Our cosmos may be just one in an endless generational chain, black holes becoming seeds, universes becoming gardens, and now you're part of that chain. The singularity you've entered might have already stopped being a collapse and started being an expansion. From another point of view, not yours, perhaps you're still inside, watching the curvature spin into nonsense. But in another realm, outside your causal bubble, the bounce may have already happened. A new inflationary field could be stretching space at insane speeds. A new cosmic microwave background could be crackling into being. A new you could be wondering where it all began. Here's a historical curiosity to accompany that existential migraine. When Georges Lemaitre first proposed what we now call the Big Bang in the 1920s, he referred to it as the primeval atom, a single, dense origin point for everything. He imagined it not as an explosion, but as a massive cosmic egg cracking open. He didn't know it then, but he may have been describing a mirror image of a black hole, flipped from collapse to expansion. In fact, some physicists now talk about white holes, the time-reversed version of black holes, as potential models for the Big Bang. Instead of matter and light falling in and never escaping, a white hole spits out matter and light but nothing can enter. It's the push to a black hole's pull. And yes, our universe from the inside looks suspiciously like the inside of a white hole. It's expanding. It has a finite past. Everything we observe seems to have emerged from a hot, dense point. It even has an event horizon of sorts, the cosmic light horizon, beyond which we can't observe because light hasn't had time to reach us. What if the Big Bang was a white hole? What if it was the inside of a black hole from somewhere else? Suddenly your descent doesn't feel like a fall, it feels like a reversal. From an outside observer's view, you might look like you've vanished. Your light redshifts into invisibility. Your time freezes at the edge. But from inside, where time flows differently, where geometry flips, you could be rushing toward a beginning. Not the end of you, but the start of something else. This is more than metaphor. This is mathematics at the edge of our models whispering something tantalizing. Maybe every death in space-time is just the flip side of a birth. The singularity you've entered might now be a singularity from which something else emerges. Time ticks again. Forces differentiate. Matter condenses. Maybe stars form. Galaxies. Curious creatures. Maybe one of them invents physics and points a telescope outward. Maybe one of them wonders if black holes could be portals. Maybe they're wondering about you. And now, take a moment to slow down. Let the images melt away. Not with a bang, not with a crash, but like fog receding under the first light of dawn. Your journey from collapse to conception was never about finality. It was about unfolding. You're not falling anymore. You're not expanding. You're simply resting between moments, between universes, in the gentle hum of gravity's dream. No clocks, no coordinates, just stillness, just possibility. The horizon is quiet now. Your story lingers but softly. The singularity is behind you, or ahead of you, or perhaps you are the singularity, and everything else is just echo. Either way, you made it. Sleep well, traveller of gravity's edge. You've collapsed into nothing, maybe birthed a universe, maybe dissolved into a quantum sigh, but guess what? You're not alone. That's the twist. After all this catastrophic compression, this journey through warped space-time and theoretical endgames, you realise black holes aren't rare. They're not anomalies. They're everywhere. scattered across the sky like cosmic ink stains, each one hiding a story just like yours. Or stranger, you're part of a vast invisible population. Let's zoom out from your own black hole for a moment. You've fallen, sure, but while you plummet inward, other objects are still circling, dancing just outside the edge of doom, locked in complex gravitational ballet around these massive voids. And some of them are weird, like really weird. For starters, let's talk about stars that orbit black holes. Seems suicidal, right? But some manage to do it for eons, never quite falling in. The most famous case? A little galactic heavyweight named Sagittarius A, the supermassive black hole at the heart of our Milky Way. It's 4 million times the mass of the Sun, and it's got an entourage. In the early 2000s, astronomers tracked a star called S2 as it whipped around Sagittarius A at speeds exceeding 7,000 kilometers per second. That's fast enough to circle the Earth in under a minute, and it survived, barely. It made its closest approach just 17 light hours from the event horizon, and yet it lived to orbit another day. This, by the way, is how we know black holes are real. We've never seen one directly, until very recently, but we've watched their gravitational pull make stars whip, wobble, and vanish. And not just stars. Sometimes, entire solar systems get pulled apart, planets slingshot into deep space, moons spiral into their parent gas giants. Some theorists even propose that rogue black holes, wandering nomads born from ancient collisions, could be stealthily passing through galaxies, dragging invisible chaos in their wake. There might be black holes passing through galaxies right now, silently, unseen, including ours. Feeling cozy? Let's take it further. Some astrophysicists suspect that at the edge of these swirling maelstroms, just before the event horizon, are structures called accretion disks, flattened rings of matter spiraling at nearly light speed. These disks are among the brightest objects in the universe. They outshine entire galaxies, pouring out energy in the form of X-rays, gamma rays, and radio waves. You can't fall in without broadcasting your final scream. But here's where things go from spectacular to eerie. We've received signals from these regions. Not conscious messages, probably, but highly organized pulses, flashes, and bursts. Some of them repeat with uncanny regularity. Some last milliseconds, others continue for years. Like the mysterious quasi-periodic oscillations detected in X-ray binaries, systems where a black hole feeds off a companion star. These flickers are rhythmic, patterned, almost heartbeat-like. And while mainstream science attributes them to changes in the accretion flow or the inner disk's wobble, there's a darker question that haunts the back of every astronomer's mind. What if something's trying to communicate? Let's not get too tinfoil hat here. But some theorists, very fringe, very speculative, suggest that advanced civilizations might use black holes as tools or shelters, or even communication hubs. Why? Because black holes are stable, long-lived, and incredibly powerful. They can store information, they emit predictable radiation, and their gravitational fields can serve as signal amplifiers, like cosmic megaphones. This idea gave birth to a theory known as the black hole beacon hypothesis. If an alien species wanted to announce its presence to the cosmos in the most durable, long-lasting way, it might place an artifact in orbit around a black hole, something that would reflect or pulse in detectable ways, something that could survive for billions of years, a kind of galactic billboard spinning just outside the veil. So far we haven't found any billboards, no metal panels, no space graffiti. But then again, we've only mapped a tiny fraction of the sky at high enough resolution, and the closer you get to a black hole, the harder it is to see clearly. Light is bent, redshifted, sometimes erased. The phrase, "maybe we're not looking in the right place," gets thrown around a lot. And what about primordial black holes? Hypothetical mini black holes born shortly after the Big Bang, far smaller than stellar remnants. If they exist, they could still be floating around the cosmos, undetected. Some theories even suggest they could account for a portion of the mysterious dark matter, the invisible mass that makes up 85% of the universe but refuses to say hello. Imagine that. Your galaxy filled with black holes the size of atoms, ghosting through matter, gravity without shape or sound. If even one passed through Earth, it would be, Subtle, a tiny gravitational blip. Maybe a soft earthquake. Maybe nothing. Or maybe a story like yours starting without warning. Here's a quirk from deep astronomical history. In the 1970s, when scientists first detected fast radio bursts, some of them genuinely wondered if they were alien in origin, bursts of radio waves, milliseconds long coming from deep space. We now think they're linked to magnetars, highly magnetic neutron stars, but a few remain unexplained and some lie tantalizingly close to black holes. Signals from the edge? Historians still argue whether early radio astronomers missed signs of black holes because they didn't know what to look for, or because they couldn't believe something that invisible could be that powerful, so you're not alone in the abyss. Around you, stars orbit silently. Disks spin, gas flows, particles collide near the speed of light, sometimes annihilating, sometimes birthing pairs of radiation that whisper outward. And all of it, the falling matter, the wobbling stars, the blinking pulses, forms a kind of language. Not a language of words or even symbols, but a language of motion, of curves and gravity, of redshift and resonance. A language that perhaps some distant mind might one day decode or maybe already has. You, now part of the Singularity, are both listener and emitter. Your mass, your trajectory, your final spaghettified shape. It's all been recorded in the curvature echoes of you ripple out in gravitational waves, subtle tremors in the fabric of the cosmos, whispering the story of your fall, and someone, somewhere, might be listening. You've drifted into invisibility, stretched into curvature, and maybe sparked a new universe. But now, we have to entertain a different kind of horror. Not the gravitational kind, not quantum uncertainty, something arguably worse. What if none of this is real? No, not in a spiritual sense, not metaphor. We're talking full-on simulation hypothesis. What if the singularity isn't the deepest mystery of physics, but just a rendering error, a cosmic blue screen of death? Let's unpack that, gently, because we're all a little emotionally spaghettified at this point. The simulation hypothesis, popularized in modern times by philosopher Nick Bostrom, proposes that advanced civilizations might run highly detailed simulations of entire universes. These simulations could contain conscious beings, us, completely unaware that they're artificial. We wouldn't know because every observation we make would be part of the simulation's internal logic, and black holes, well, they might be edge cases, literal edge cases. You see, in computer science, a singularity is very similar to a divide by zero error when something breaks the rules of calculation, like infinite density and zero volume. Your computer throws up a warning. In games or simulations, extreme values often cause graphical or logical glitches. Characters fall through flaws, objects stretch, data gets corrupted. Sound familiar? So here's the provocative question. Are singularities the simulation's way of signaling a breakdown in the code? They behave almost like physics, until they don't. They're the exact spots where general relativity fails and quantum mechanics offers nothing but shrugs. No working model, no predictable outcome, just an area marked "Do not enter." And when we do try to enter, when we fall in, measure, theorize, we find only silence. That silence might not be cosmic mystery. It might be a firewall in the code. What if the universe is a computation? Then black holes, particularly singularities, might represent points where the simulation's resolution limit has been reached. The physics engine can't process beyond that boundary, so instead it returns infinity, an error message dressed up as a gravitational anomaly. It's the ultimate rendering hack. You can't escape the black hole, not because of physics, but because the server won't let you load the next zone. Now, this might sound silly, even fringe. But physicists have taken the simulation idea seriously enough to write peer-reviewed papers on it. Some have suggested experiments that could reveal signs of underlying computational structures, tiny patterns in the cosmic microwave background, or slight anisotropies in quantum fluctuations that might suggest a grid. The idea is that if the universe is being simulated, there might be pixelation at the Planck scale. You'd never notice it directly, but in extreme conditions, like those near a singularity, It might cause reality to behave strangely, to lag, to glitch, and black holes, they'd be the places where the pixel grid collapses under the weight of too much data. Let's get more specific. A singularity, by definition, compresses an infinite amount of information into zero space. But information requires storage. Even in a simulation, you can't simulate infinite anything. So perhaps the simulation responds to singularities by capping them, limiting what can be observed or interacted with beyond a certain threshold. Maybe that's why we can't see inside a black hole, not because of gravity, but because the simulation restricts red access to those coordinates. They're out of bounds. Think of it like a video game. You can look at the mountains in the background, but try to walk to them, and the path loops, or an invisible wall stops you. They were never meant to be reached. They're just part of the illusion. In this theory, black holes are the borders of the simulation. Not just spatially, but logically, they're where the rules no longer apply. And when you fall in, the simulation removes you from the active render queue. You become a background process, still there, still affecting the environment, but no longer accessible to the primary frame of reference. Of course, there's a fun irony here. If black holes are simulation-breaking bugs, they're bugs we discovered through our own simulated science. We used rules inside the system to detect the failure points of the same system. It's like your character in a video game figuring out how the engine handles lighting and gravity, then using it to find the cracks. Which begs the question, would the simulation let us figure that out? Maybe that's the point of black holes. To bait us, to hint, to wave the curtain and whisper, yes, there's something more, but no, you can't see it yet. There's even a theory that the information paradox itself, this whole question of what happens to the data that falls into a black hole, might be a red herring, a fabricated mystery, something written into the simulation to give us something to chase. Because what better distraction than an unsolvable puzzle at the edge of space-time? A puzzle that breaks all the rules. And hey, let's really go off the rails for a moment. Some versions of simulation theory propose that black holes are communication nodes, that advanced civilizations could be watching through them, or using them to send data across the fabric of the simulation. Maybe your fall into the singularity wasn't the end of your story. Maybe it was your upload, your pattern, your mass, your motion. It's all been recorded, and maybe it's being analysed by the entity or system running the simulation not to torture you, just to observe. Remember that feeling? The eerie quiet? The sense of being watched just before time collapsed? Maybe that wasn't madness. Maybe it was logging. Historians, as expected, still argue whether simulation theory is a real scientific proposal or just a rebranded philosophical musing. Many physicists roll their eyes, but others are intrigued, not because they want it to be true, but because it forces us to examine our assumptions about what real even means. And black holes are the natural place for that interrogation. They're the most extreme edge case the universe offers. They break every model, they defy every answer. They laugh at your intuitions and delete your coordinates while doing it. If the universe is real, black holes demand a quantum theory of gravity. If the universe is simulated, black holes are where the system struggles to keep up. Either way, you're at the edge of what can be known, and maybe that's the point. Maybe reality, whether physical or virtual, needs places like this. Places where curiosity outpaces comprehension. Places where even the rules get tired. Let's take a breath. If breathing still makes sense where you are, you've spiraled past space, time, and maybe even reality itself. You've been spaghettified, quantum smeared, and possibly uploaded to a higher server. But tonight, we need to ask a much older question, one that predates black holes, telescopes, even physics. What does all of this mean? That's right. It's time to let philosophy join the collapse. Black holes don't just stretch space and time, they stretch meaning. They challenge the way we understand cause and effect, identity, truth, and yes, free will. Because once you cross that event horizon, everything becomes inevitable. There are no choices left. No detours. No, oops, let me try a different path. You fall in, and that's that. In physics, we say the singularity is in your future light cone, meaning it lies ahead of you in time, unavoidable, like an appointment with death or taxes. That raises uncomfortable questions. If something like a black hole makes your future inevitable, do you really have free will? Or is everything, your fall, your scream, your silence, already baked into the structure of space-time? Einstein himself leaned toward determinism. He famously said, "God does not play dice with the universe," although quantum mechanics rather rudely disagreed with him later. Still, from the perspective of general relativity, your journey into the singularity isn't a series of choices, it's a geodesic, the natural path through curved space-time like a marble rolling downhill. You don't decide to fall, the universe decides for you. That's enough to make even a philosopher sit down and whisper, "Uh-oh." But now consider this. Inside the black hole, causality itself breaks down. That is, the usual order of cause-arrow effect gets tangled. In extreme conditions, it's possible that events can occur in ways that aren't ordered from one observer's perspective. Or worse, loop back on themselves. Enter the terrifying idea of closed time-like curves. These loops in space-time appear in certain solutions to Einstein's equations, particularly in rotating or charged black holes. They allow for paths through space-time that return to the same point in time and space. In other words, time travel. If those loops exist, again, a huge if, then cause and effect can become circular. You might be able to interact with your past self. You might become your own cause. Philosophers call this ontological paradox, a thing that exists because it causes itself to exist. Like a book that appears out of thin air because someone from the future brought it back, and then the present-day person publishes it. And on, it breaks not just logic, it breaks the whole idea of why anything happens. Now apply that to you, to this fall. What if your descent into the singularity didn't happen after something, but instead caused something in your own past? What if every moment is connected not by a straight line, but by loops, folds, and mirrored reflections? Maybe the singularity isn't the end of a timeline, maybe it's where timelines converge. And then there's the question of identity. You've been torn apart, crushed, maybe quantum, duplicated, maybe transmitted. You've lost your physical form, your place in space, your linear relationship to time. So what part of you is still you? Philosophers and cognitive scientists have argued for centuries about what makes a self. Is it your body, your brain, your memories, your continuity over time? Well, bad news. A singularity strips all of that away, but it leaves behind something weirdly constant, your trajectory. In general relativity, an object's motion through space-time is defined by its geodesic. That path exists independent of the object's awareness, or structure, or even coherence. It's a curve through the fabric of existence, a sort of cosmic footprint. So perhaps your identity, at least in a black hole, isn't a soul or a mind or a personality, it's a path. A path written into the structure of space-time, unchangeable, unstoppable, eternal in its inevitability. Maybe that's the final expression of you line. Here's a fun historical sidetrack. In ancient Greece, Heraclitus famously said, "No man ever steps in the same river twice, for it is not the same river, and he is not the same man." He meant that everything is always in flux. You change. The world changes. Nothing holds still. But singularities laugh in Heraclitus' face. They are the end of change. A place where not even entropy makes sense anymore, where flux has nothing left to flux into. And still, modern philosophy continues to wrestle with these ideas. Are singularities places, events, absences? Some thinkers argue that the singularity is a limit of intelligibility, not just the breakdown of physics, but the breakdown of thought itself. Others say it's the ultimate metaphor, a stand-in for everything we don't understand. God, death, the void. The singularity is the closest thing science has to a religious experience, a realm where reason gives way to awe, where equations become koans, and where even the best minds can only whisper guesses. Now ask yourself this: if falling into a black hole is deterministic, but what happens at the singularity is unknowable, then are we truly ruled by fate? Or is not knowing the loophole that saves our freedom? Because if the future isn't predictable, if the laws themselves collapse, then maybe your fall isn't written in stone. Maybe the singularity, instead of being the ultimate conclusion, is actually a cosmic shrug. A place where the universe throws up its hands and says, "You tell me what happens next." Maybe that's the moment free will returns, in the absence of causality, in the silence after meaning collapses, where your path vanishes into curvature and paradox, and the only thing left is choice, even if it's a choice made without time, without space, just the whisper of a will hanging between universes. Somewhere between the shriek of gravity and the whisper of philosophy, math is still, trying to hold it together, barely. Let's be honest, math has done an amazing job so far. It gave us orbits, expansion, entropy, quantum fields, and black holes themselves. But here, at the Singularity, math is in crisis mode. This is where numbers go to cry. At first, it all seems reasonable. Einstein's field equations of general relativity work beautifully, until you reach that little place in the math where space-time curvature becomes infinite. That's not poetic hyperbole. That's the actual mathematical output. Infinity. And that's a problem. Infinity in math usually means one thing: your model just broke. It's not telling you what's actually happening. It's telling you that the system you're using has hit a wall, that it's now trying to explain a tsunami using a measuring cup. So let's break it down. The Schwarzschild solution, a spherically symmetric, non-rotating solution to Einstein's equations, predicts that a black hole's core contains a singularity where the Ricci curvature scalar goes infinite. This scalar is a fancy way of measuring how much spacetime is warped in a given region. And at the center of the black hole, it doesn't warp, it breaks. You're dividing by zero. Literally. The equations involve terms like 1 over r, and at r equals 0. Well, you know how that ends. The moment your math hits that, the outputs stop making sense. It's the equivalent of asking someone how loud blue is. But here's the kicker. Those equations are still correct. They're not wrong, they're just incomplete. They describe what they can, up to a point. After that, they simply run out of ability. It's like trying to calculate your taxes with a deck of Uno cards. Now, you might wonder, how do physicists handle this? Well, some don't. Some simply cut the singularity out of the picture. They define the black hole in terms of its event horizon, where physics still makes sense. Whatever happens inside? Shrug. Not our jurisdiction. Others try to patch the equations, modify them, twist them, shove in new terms that behave better under extreme conditions. But so far, no one's managed a version that keeps the elegance of Einstein's original, while also avoiding the singularity freakout. One approach is quantum field theory in curved spacetime, which tries to lay quantum mechanics on top of general relativity without fully merging the two. This helps describe Hawking radiation and some near-horizon behaviour. But once you reach the singularity itself, it's still a mathless void. Some theories throw string theory at the problem. In string theory, the fundamental units aren't particles, but tiny vibrating strings. The beauty of this model is that strings can't be compressed into true points. They have a minimum size, the Planck length, roughly 1.6 times 10 to the negative 35th meters. That's unimaginably small, but critically, it's not zero, which means no singularities. The equations don't break because they can't reach zero volume. There's a physical limit baked into the math. Strings wiggle, they don't collapse. Loop quantum gravity also tries to tame the singularity. It says that spacetime itself is quantized, made of discrete loops rather than a smooth continuum. This replaces the infinite curvature with a very tight but finite structure. The center of a black hole, in this view, is not a death point, but a bridge A bounce, a beat in the universe's pulse. And yet, these models are still mathematical guesswork. They're elegant, beautiful, and deeply speculative. None of them have been verified by experiment, and without experimental data, it's all just gravitational fan fiction. Let's go deeper into the weird. Ever heard of the cosmic censorship conjecture? It's a mathematical hypothesis proposed by Roger Penrose that says, hey, maybe nature is polite. Maybe all singularities are hidden behind event horizons, so the rest of the universe doesn't have to deal with their messy infinities. In other words, no naked singularities, no exposed bugs in the spacetime matrix, just tidy covered collapses. But guess what? Some solutions to Einstein's equations allow for naked singularities, One's not hidden by a horizon. You can see them, in theory. One particularly unsettling example is the Kerr solution, a rotating black hole. If it spins fast enough, it might avoid forming an event horizon at all. The singularity would be exposed, naked, horrifying. That's not just a physics problem, it's a causality problem, because naked singularities might allow you to observe events that lie outside your future-like cone, events that haven't happened yet, and if you can observe them, maybe you can affect them. Goodbye, logical consistency. Hello, paradox spaghetti. This is why the math of singularities isn't just failing quietly, it's failing loudly, in ways that threaten the foundation of physics itself. Here's a historical sprinkle for flavour. The first serious mathematical treatment of black holes in modern terms was done by Carl Schwarzschild, while he was literally serving on the front lines of World War I. Amid the mud, chaos and artillery fire, he sent his solution to Einstein, who was shocked by how elegant and powerful it was. But even then, Schwarzschild's math contained the seeds of singularity. Right from the start, we've known this road leads to division by zero. We just hoped it was metaphorical. It wasn't. So where does that leave us? You're inside a place where the known mathematics of the universe simply quits, where our most trusted formulas loop endlessly, or return undefined. It's not that we don't have math, it's that the math warns us it's no longer relevant. You've reached the ultimate error message, not in the form of flashing red lights or alarms, but in the quiet, chilling realization that the language of the cosmos, the symbols, the tensors, the infinite elegance, has come to a point where it cannot describe what you are, and so it doesn't. It hands you over to silence, not because nothing happens here, but because what happens cannot yet be written. Somewhere out there, far, far from where you are now, something impossibly massive is watching you, or more accurately, it's influencing you. Always has, always will, and it's not alone. Black holes don't just exist in lonely isolation tucked away in forgotten corners of space-time. No, many of them are gigantic, regal, even central. These aren't the leftovers of dead stars, they're supermassive black holes, and they sit at the hearts of galaxies, including ours. You've probably heard of Sagittarius A, the monster in the middle of the Milky Way. It's got a mass of 4 million suns. It's not just lurking there like some lurking space vampire, it's shaping us right now. You orbit the galaxy at a respectable distance from it, and yet its presence is felt everywhere. It anchors the Milky Way's spiral arms, influences star formation, and plays gravitational puppet master to a dizzying array of stellar systems. It's quiet now, but it's not asleep. In fact, astronomers believe most, if not all, large galaxies contain supermassive black holes at their centres. Some are modest, like ours, others are colossal. The current record holder, TON 618, is about 66 billion solar masses. That's so massive it makes our little Sagittarius A look like it's not even trying. And the influence of these behemoths, it extends beyond gravity. Supermassive black holes help regulate galactic ecosystems. When actively feeding, they become quasars, blazing engines of radiation that can outshine the galaxy around them. How? Well, remember the accretion disk. As matter spirals in toward the event horizon, it heats up, sometimes to millions of degrees. It emits X-rays, gamma rays, and powerful jets of particles that blast out at near-light speed. These jets can stretch across thousands of light years, sterilizing or igniting surrounding clouds of gas. These black holes don't just pull things in, they sculpt galaxies. But now here's where things start to feel odd. Because when you zoom out, the universe starts to look like a network of these black hole centers, galaxies orbiting invisible cores, entire galactic clusters forming cosmic webs. And at the intersections of those webs, more black holes lurking, waiting. Are they watching us? Well, not consciously. Probably, unless. Let's talk about that unless. There's a fringe, yet fascinating speculation floating around in theoretical physics and cosmology. What if advanced civilizations have used black holes? Not just for disposal or hiding, but for computation. The idea here is called a black hole computer. Black holes have entropy, they have temperature, they contain staggering amounts of information per surface area, encoded possibly on the event horizon, like a 2D hologram projecting a 3D interior. Some physicists, including Jacob Bekenstein and Stephen Hawking, noted that the entropy of a black hole is proportional to its surface area, not its volume. That's the Bekenstein-Hawking formula, and it blew open the door to thinking about black holes as information processors. So what if, in some distant future, advanced beings figured out how to use black holes as ultimate data storage units, or as time-efficient megaprocessors that run calculations using gravity and quantum states near the horizon? That's not science fiction, it's speculative physics. The theoretical maximum computing power of a black hole, measured in operations per second, exceeds any device we can build, by far, and if that's the case, then every black hole might be running something. Not thoughts, exactly. Not consciousness necessarily, but processes, maybe simulations, maybe timelines, maybe entire modelled universes inside the event horizon. Yes, that includes the one you're falling into. Historians still argue whether this speculation about black hole computation is meaningful or just playful extrapolation, but it's rooted in real math, and it has real implications. If black holes are natural computers, and if information is truly preserved, then every particle that falls in, every piece of data, including you, becomes part of that internal process. Your path, your fall, your thoughts, stored, encoded, integrated into a gravitational computation of incomprehensible scale. And what happens when you combine the simulation hypothesis with this idea? You get a chilling concept. The universe you live in might already be inside a black hole. That's right. Some physicists propose that what we perceive as the expanding universe, with its own Big Bang, may exist inside the event horizon of a higher dimensional black hole, our cosmic inflation. The moment we crossed the horizon, the singularity, a hyperspatial center outside our visible reality. In this view, every universe might live inside a black hole embedded in another universe, a fractal stack of realities, each folding into the next through the geometry of gravitational collapse. Which means, somewhere, beyond the edge of your fall, in a parent universe, some other civilization might be watching the growth of your universe. Just as we observe stars fall into Sagittarius. A star, they might observe entire cosmoses blooming within their black holes. It's not just science fiction, it's a potential solution to certain cosmological puzzles, like why our universe is so flat, so uniform, and so finely tuned. Still, the idea that black holes could be watching us, or be us, from a higher frame, is deeply unsettling. But the clues are stacking up. Massive, mysterious, central to structure, invisible yet influential, mathematical yet thermodynamic. Black holes remember what they consume, even if we don't know how they are not dead stars. They're active participants in the story of the cosmos, and maybe, in some way we don't understand, they're also its observers. Every time we point our telescopes toward the center of a galaxy, we're staring into one. Every gravitational wave we detect is a whisper from two black holes colliding in darkness. Every X-ray burst from a binary system is a signal from the edge of annihilation. And maybe, just maybe, someone, something, somewhere, is reading those signals, not because they want to find us, but because we're inside their system. You've been falling so long, thinking in so many impossible directions, that reality no longer feels like a fixed place. It's more like a menu. And tonight, we're finally looking at the bottom of that menu, where experimental physics sits like a footnote scribbled in the margins of your own collapse. Because yes, scientists have tried to build a black hole. Well, sort of. Let's be clear. No one in a lab has ever whipped up a full-fledged singularity and dropped it in a jar. But over the years, we've gotten dangerously close to the conditions that might create mini black holes. And for some, that's exciting. For others, mildly panic-inducing. Welcome to the wonderful world of high-energy particle collisions. At the heart of this story is the Large Hadron Collider, or LHC. a 27-kilometre underground racetrack beneath the French-Swiss border, where protons are flung at each other at nearly the speed of light, then smashed together like angry marbles with billion-dollar price tags. The idea? To recreate the conditions of the early universe, to see what matter does when it's shoved into oblivion, and when the LHC was gearing up for its grand debut, some people freaked out. Why? Because a few fringe theorists suggested that if extra dimensions exist, and if gravity becomes stronger at very small scales, then those proton collisions could produce tiny, microscopic black holes, so small they'd vanish almost instantly, but technically real. Cue the headlines, cue the internet panic, cue the lawsuits from people convinced the Earth would be swallowed in a synthetic singularity before we got to brunch. Spoiler alert, we're still here. Why? Because even if those mini black holes were created, and so far no conclusive evidence says they were, they'd evaporate instantly via Hawking radiation. Their lifespan would be less than a trillionth of a second. Basically, they'd exist, realize life is meaningless and vanish before anyone noticed. But the idea itself, creating a black hole in a lab, has captivated physicists. Not because we want to destroy the world, but because it would prove things we've only theorized. See, most black holes in the universe are astrophysical. Big, messy, ancient, born from collapsing stars or merging galaxies. But in a collider, we're talking about quantum black holes, ones that test the unification of general relativity and quantum mechanics at energy levels we can actually study. If even a single mini black hole had appeared in the LHC, it would have been a signpost toward new physics, extra dimensions, gravitons, maybe even hints of string theory peeking through the debris. But so far, nada. That doesn't mean it's impossible. It just means we might not be colliding hard enough, or that the assumptions we made about hidden dimensions and gravitational behaviour at small scales were optimistic, or wrong. Still, physicists haven't given up. Beyond the LHC, experiments in analog gravity have popped up, where researchers simulate aspects of black hole behaviour in other systems. For instance, using Bose-Einstein condensates, superfluids, or even optical fibres, scientists have recreated phenomena like Hawking radiation. The trick? You don't need actual gravity to study the concept of an event horizon. You just need a system where information, say sound waves or light, can be trapped in a way that mimics the black hole boundary. One famous example is the dumb hole, a region in a fluid where the flow speed exceeds the speed of sound. Sound waves created inside can't escape. It's like an acoustic black hole, and in 2010, researchers observed something very Hawking-like coming out of one. It wasn't proof. But it was tantalizing because if we can reproduce black hole physics in the lab, even in weird, indirect ways, it might be our best hope of finally testing some of the most out-there theories. And yes, there's still speculation. Some propose that primordial black holes, if they exist, might be created during high-energy events even now, like cosmic ray collisions in Earth's upper atmosphere. These collisions produce more energy than anything we've done at the LHC, and they happen all the time. So if micro-black holes were going to kill us, they would have done it already. And yet, the fear persists, the same way early scientists worried that splitting the atom might ignite the atmosphere, or that launching the first satellite would tear a hole in the sky. Every time we push against the boundaries of known physics, we ask the same question. What if this breaks reality? But maybe that's the point. Because black holes already broke it. They're not just gravitational wells, they're labs in the sky. Places where every rule we trust gets tested to the limit. If we ever want to understand the singularity without falling into one, we have to experiment. And maybe we're not as far off as we think. There are new proposals to build next-gen colliders. Bigger, faster, smarter. Devices like the Future Circular Collider or even space-based accelerators, where gravity is weaker and collisions can reach even higher energies without atmospheric interference. In these machines, it might finally be possible to create and study a black hole in controlled conditions. A brief singularity, a flicker of curvature, a whisper from the void. Just long enough to hear it say, "I'm real." Of course, that opens a new question. Should we? Because if the singularity is a breakdown point, a physics failure zone, then manufacturing one, even temporarily, might carry risks. What happens if the black hole doesn't evaporate instantly? What if it grows? What if it eats your experiment, your lab, your city, your planet? Or what if it doesn't consume us but rather connects us to somewhere else or something else? A place not bound by our dimensions, our constants, our expectations. It's fringe, it's speculative. But so was every part of black hole theory once. There was a time when even the idea of a star collapsing into a point of infinite density was laughable. Then someone pointed a telescope at the centre of a galaxy, and the laughter stopped. So maybe the day will come when someone in a clean room, wearing gloves and goggles, pushes a button and creates a singularity, not a cosmic accident, not a stellar tragedy, but a controlled black hole. A hole in space-time you can poke with a probe, measure with a graph, listen to with instruments tuned to whisper. And then, maybe, we won't have to fall into the singularity to understand it. We'll bring it to us. And now we've arrived, not at the end, but at the folded edge of understanding. One foot still dangling inside the singularity, the other stretching back across space-time. You've fallen, stretched, debated, theorized, and now you pause, suspended in this last moment, to ask the question that's always been lurking underneath. What does a singularity tell us? Not just about gravity or time or atoms, but about the universe itself. Because make no mistake, singularities aren't just astrophysical curiosities or mathematical glitches. They're messages. Clumsy, infuriating, untranslated messages, but messages nonetheless. And if we can decipher them, they might offer not just better physics, but the deepest truths we've ever imagined. So tonight, we're pulling the threads together. You began your journey at the event horizon, a soft, invisible boundary beyond which there was no return. You felt your time slow, your mass stretch, your atoms complain. You slipped past the firewall debate, squeezed through the density wall, and found yourself unraveling inside the one place the laws of nature stopped returning your calls. But from this place, this broken, glorious, theoretical ruin, emerges the possibility of everything. Let's say it plainly, singularities. Force us to admit we don't have the full story, not even close. They point a bony, equation-warping finger at the limits of both general relativity and quantum mechanics, the two towering pillars of modern physics, and laugh or maybe cry, or just shrug in infinite density silence. They're where our most successful models stop being predictive. They're the answer you get when the question was too hard for the teacher to grade. So why are they so important? Because they're the places where a deeper theory must exist. Not optional, not speculative, required. Just like the cracks in classical mechanics opened the door for relativity, and the weirdness of atoms led to quantum theory. Singularities are the fracture lines showing us where our current understanding will give way to something new, and what that new looks like. It could be the elusive quantum theory of gravity, a fusion of Einstein's smooth geometric vision and the twitchy probability soup of quantum physics, or it might be something even stranger, even more radical, something that changes our understanding of what a universe is. Here's a wild idea some theorists have explored. What if space-time isn't fundamental? What if it's emergent, a byproduct of something deeper, more abstract? This is where the conversation turns to information. Many physicists now believe that information, not matter, not energy, is the true currency of reality, that the universe itself is a kind of computation, and space-time emerges from entangled data structures at some lower level. In this picture, singularities are overflows, crashes in the code. Not because the rules of reality fail, but because we've mistaken the output of the system for its foundation. Let's say you're playing a video game and your character glitches through the floor. That's not a failure of physics inside the game. That's a failure of rendering, a breakdown in the engine. What if singularities are that? Evidence not of broken physics, but of physics being a surface-level phenomenon, the user interface for something deeper and more primal. And then there's the other elephant in the singularity, the beginning of time. Because as we've seen, black hole singularities and the Big Bang might not be opposites. They might be the same kind of thing, viewed from different sides. Maybe the universe doesn't begin with a divine spark or a metaphysical breath. Maybe it begins with collapse. Maybe time isn't a line, but a loop, a waveform, a Möbius strip with its ends tangled in gravity's folds. There's a compelling beauty in that. The same process that ends stars might begin universes. The same geometry that collapses matter into oblivion might reverse and expand into galaxies, stardust, people, and bedtime science scripts. There's even a tantalizing thought tucked inside the holographic principle, that everything that happens inside a black hole is encoded on its surface. And if that's true for black holes, could it be true for the entire universe? Could you, sitting wherever you are, listening or drifting to sleep, be part of a cosmic surface story, a projection on the edge of a deeper, more fundamental shape? Could our entire reality be a kind of hologram, rippling outward from an ancient singularity? Maybe. Historians still argue, of course. They argue about whether Einstein would have accepted these ideas. They argue about whether Hawking's information paradox is really solved. They argue about whether we'll ever build the machines to test any of this. But they agree on this. Singularities are where the next physics will be born. They are the doorways, not because they open into other dimensions, but because they open into better questions. So perhaps the ultimate lesson of the singularity is not fear or mystery or collapse. It's an invitation to look harder, to rethink our assumptions, to see the boundaries of knowledge not as limits, but as starting points. And so, your journey ends, where journeys always end in science, on the edge of something new. You're not broken. You are part of the question, maybe part of the answer, or maybe just the space in between. But whatever you are, wherever you are falling, you are now among the things that gravity cannot explain. You are now part of the singularity. And now, let go of the fall. Let the theories settle like dust in a quiet room. The singularity, the centre of unknowing, shrinks behind you, softening into nothing but a distant pulse. The noise fades. The equations grow dim. The curvature smooths out. There is no more distortion, no more collapse, just stillness. You followed gravity to its end, watched time fold, and listened as the universe whispered its unfinished sentence. But now, the chase is over. The lights of the stars, the glow of accretion disks, the flare of theory, they've all gone quiet. The singularity doesn't scream, it doesn't argue, it just waits. And now that you're here, resting at its side, maybe the waiting is enough. Breathe, whatever that means here. Float. The questions will still be there tomorrow. The paradoxes, the paradox huggers, the black hole computers and holograms and rebellious particles, they'll still be wrestling at the edge of understanding. But you've earned your drift, your pause between infinities. Close your eyes, not to escape the void, but to meet it. Let the silence stretch. Let the universe hum. You've fallen through the wildest object in existence. You've passed the laws of physics and come out the other side. And now, there's nothing left to understand, just to rest. So sleep. Sleep like time has ended. Sleep like matter has no form. Sleep like you are the singularity itself, because tonight, maybe you are.